So this is 4.4 curve sketching. So we will apply the information that we just learned in the previous two sections to basically graphing functions. But maybe before we do that, I will summarize the information we learned. Okay, so first we talked about first derivative. So first derivative. And yeah, first derivative was associated or came with critical numbers. So let's make it now the first point. So critical numbers. Numbers are points. And let's make the first comment, they must be in domain. So must be in domain. Right, so they must be part of the function, right? If I have maybe something like a quick example. So let's say 3x divided by x squared minus 9. Okay, so yeah, so there are two numbers that are not in that domain, right? So that would be numbers that would give me 0 in the denominator. So that would be 3, negative 3, right? So you can't, those two numbers cannot be critical numbers, critical points, because they're not in the domain. Okay, so what are those critical numbers? They're basically, right? So we would take a first derivative of the function, and then we would make it equal to 0 and solve it for x's. So these are zeros of first derivative. So f prime of x. So right, if we had a function, we would take a first derivative, which is derivative, make it equal to 0, and solve it. So that's the first source of those critical numbers. And the second source is where the function, or f prime actually, derivative, where, let's just do it this way, where f prime of x is just one prime. Okay, let me try again. Okay, f prime of x is undefined, doesn't exist. Okay, so we have two sources of those critical numbers. And yeah, so the second thing that I want to remind you about is what that first derivative is used for. So there are two things. The first one is whether the function is decreasing. Right, helps us determine that. Decreasing, this is E, I'm trying to make it better. Decreasing or increasing. Okay, and basically when first derivative is greater than 0, so let's make it like this. So f prime of x is greater than 0. And the conclusion is the function is increasing. And then when the first derivative is less than 0, the function is decreasing. Okay, so that was the first 2 points I wanted to make. The third one is that first derivative test. Okay, let me organize my things here. Okay. So the last thing is the first derivative test. So let's write it here. So first derivative test. Okay, so that was right when we have those critical numbers, when we find them, and then we were putting those critical numbers on the number line, and we're trying to decide whether the function is positive or negative. And then we were concluding, right, if the function changes from going down, right, or from decreasing to increasing, right, we'll obviously have minimum here, and then if we have it this way, right, we will have maximum. Okay, so let me write it here. So we have if at critical number f prime or f switches from maybe let me just do it this way. And if we have this situation from increasing to decreasing, then we have maximum. And so that was that. The switch from increasing to decreasing. And then when we have it, so that's our first, that's the second. Similarly, right? So if the same thing. So this time it's from decreasing to increasing. So we have minimum. Okay, so that's the first derivative. So now the second derivative. So second derivative, similarly. Second, let me make it consistent. So let's write it this way. Second derivative. Okay, and similarly, right? We'll do. We'll go through those 3 points. Okay, so inflection points. Okay, yeah, so inflection points, just kind of quickly to remind you, right? So we have a function, looks like this, right? So that inflection point would be a point where the function changes concavity, right? So you see that, and so that's the inflection point, concave down and then concave up, right? So inflection point would be the point where the function changes concavity. Okay, so yeah, and we get those points in a similar way, right? So we have, but this time, right, we have the second derivative. So we have zeros of that second derivative. So that would give us, most of the time, right, give us those inflection points, but sometimes it wouldn't. So potentially. Okay. So yeah, so we just take that second derivative, f double prime of x, and make it equal to 0. And then we solve So that's one source. The second source is where the function or that second derivative is undefined. So similarly to that first derivative and critical numbers, critical points. So where f double prime of x is undefined. Okay, so the second derivative tells us about concavity, right? We get information from it about concavity. Concave up, concave down. Okay, so we have concavity. And yeah, it works in this, right? It's pretty intuitive. So when that second derivative is greater than 0, then we have concave up. If it's less than 0, concave down. Okay, so then similarly to that first derivative, right, we have second derivative test. I think let's just make it regular white. So second derivative test. And well, basically, I'll give you in a moment more information, but basically when the concave is up, we have a maximum. When the concave is down, we have a minimum. Okay, and the way we use it is we find the critical numbers, right? So we have them usually already from that first derivative. So find critical number c, and then we evaluate that second derivative at that number. So evaluate f double prime of c. And now if f of c greater than 0, we have minimum, right? Because we have, right, that concave is down. Now if f of c is less than 0, maximum. Okay, so that's the second derivative test. Okay, so now, yeah, so that was a summary, right, of those two, first derivative, second derivative, what kind of information we can get from those two. And now, yeah, let's use it on a concrete example. So example 1. And, well, we just have to sketch a graph. And the function f of x is, it's a rational function. So we have 2, then at the top we have x squared minus 9, and the bottom is x squared minus 4. Okay, and yeah, if you want, you can calculate those derivatives, but I'm just going to give them to you. So the first one is, the top is 20x, and the bottom is x squared minus 4, and it's squared. Okay, so that's the first derivative. The second derivative, f double prime of x, it looks like this. So it's negative 20. And then we have 3x squared plus 4. Okay, and then the bottom is x squared minus 4 to the third power. Minus 4 to the third power. Okay, so yeah, we'll start with with x and y intercepts. So number one, first step, intercepts. All right, so we'll use kind of skills and information that we learned in pre-calculus, hopefully, and also in calculus. All right, so we'll do intercepts, then symmetry, asymptotes, and then we'll look at that first and second derivative, and then we'll graph it. So first one is intercepts. So let's start with x-intercepts. So x-intercepts, and I always like to write it, right? So for x-intercepts, y is equal to 0. Okay, so I'll take that original function. Okay, so that was looked something like this. I mean, exactly like this. So x squared. I'm not going to solve it for you. Just mention that, right? To get those intercepts, you just kind of think about. We can solve it algebraically, but basically, right? So the denominator will never give you the intercepts, right? Because these will be asymptotes, right? These are so that 2 and negative 2, right, which will 0 the denominator, are not going to give you the intercepts, right? Because function is undefined at those two numbers. So intercepts, or the zeros, right, of this function you'll get them from the numerator, right? So numerator will become 0 for x equals 3 and x equals negative 3. Right? So these are the two intercepts. Maybe let's write them just as points. So that'd be 3, 0, and this one would be negative 3, 0. Right? So we have 2 points, 2 x-intercepts, and now y-intercepts. I think I had it in green, yeah. Okay, so yeah, no more space there. So y-intercepts, intercepts. Yeah, so for y-intercept, well, x equals to 0, right? So the only thing we need to do is plug in 0 for x. So yeah, if we do that, we're going to get, okay, so we're here. If we make x equal to 0, so 0 here, 0 there, so we'll get 18 over 4, which is 9 over 2. Right, so that y equals 9 over 2. Or we can write it as a point, so 0, 9 over 2. Okay, so that's these are intercepts. The second step will be symmetry. Right, so we're using all kinds of skills. Symmetry, not sure if it's double M or single M, you guys probably know better. Anyway, so the symmetry, right, you can kind of, we could calculate it, but just by looking at the function, right, we have square here, square there. So I'm guessing the symmetry will be even, right? And if we plug in negative x, right, in here and in here, right? So I reviewed that at the beginning of the course, right? So you can look at it, you can check it. Basically, I'm plugging in negative x, right? So I'm doing f of negative x. And yeah, if I'm squaring a negative number or negative variable, or a variable with a negative in front of it, I'm just getting the same thing, right? I'm getting a positive. I hope you know what I'm talking about, right? So if I plug in that negative x in here, right, I'm getting negative x squared, so that's going to be just x squared. Same thing here. So I'm going to get the same thing as I started with. So we can conclude the symmetry is even. So this is the function will be even. Okay, so that's the that's symmetry. And then the next step is asymptotes. Okay, so asymptotes. So asymptotes. So we talked about the asymptotes a little bit, right? So we have two. The first type is vertical. And we get the asymptotes from the denominator, right? So if the zeros of the denominator is the asymptote, so and you see that I'm going through that, right? The stuff that is part of pre-calculus or algebra rather quickly. I don't want to spend too much time on pre-calculus. So now horizontal. So that was vertical. Now horizontal. So that was we can look at the function, and horizontal asymptotes, right, basically are depending on the degree of the top and the bottom, right? So you guys see the degree of the top is 2, degree of the bottom is 2. So when that happens, basically we ignore the numbers that are being added or subtracted. The only thing we care about is the leading coefficients, right, of the top polynomial and the bottom. Leading coefficient of the top will be 2, the bottom 1, right? So we have 2 over 1. So that horizontal asymptote will be y equals 2. Okay, so we have the asymptotes. And now let's focus on the calculus part. So step number 4 is critical numbers. Okay. So critical numbers, and we have that first derivative. I'm going to write it here. So that's 20x x squared minus 4 to the second power. Okay, so we make it equal to 0. We solve it, right? So if we solve it, you see that, right, we could solve it algebraically, multiply by the denominator. I would get 20x equals 0. Right, so, or we can, the way I like to think about it is that, well, what number that I put in the numerator for x would give me 0? Well, that number is 0. Okay, so that's the first critical number. And we could look at the denominator, right? Because we know that when the the first derivative doesn't exist, and or first derivative is undefined for certain numbers, in this case it's going to be 2 and negative 2, right? 2 and negative 2. Then these are also critical numbers. But the condition is that critical numbers need to be part of the domain, and they're not, right? Because domain for this function doesn't include 2 or negative 2, right? So we have, all right, let's actually write it maybe like this. So x equals 2, x equals negative 2, and let's just cross them like this, not in domain. Okay, so let's look at that first derivative. So step number 5. Let's make it white, just regular 5. So first derivative analysis. And yeah, so let's write down that first derivative. So that's f prime of x. Right, so that was 20x. And the bottom was x squared minus 4. And this was to the second power. Okay, so we had... okay, so we have the first derivative. And yeah, number line. And yeah, so we have only one critical number. I think, yeah, it's 0. So let's put that 0. I think I was making them blue, right? So 0. And I also will put those two numbers that are not critical numbers, but these are asymptotes, right? So so we'll get pretty useful information from those two numbers as well, right? So from the -2 and 2, because yeah, so when you have an asymptote, the function usually changes the shape or the direction, right? It becomes increasing from decreasing, etc. Well, I'm not sure if that will happen in this case, but we'll see in a moment. Okay, so so we have those they're not really critical numbers, but anyway, this was supposed to be red. All right, so next thing was, and now everything disappeared. Next thing, let's pick those testing numbers. Right, so -3, -1, 1 here, +1, and 3. Okay, so we just check it for those testing numbers, and yes, I'm looking at this, right? I'm looking at the sign of that first derivative for those 4 testing numbers, right? So I'm trying to figure out what this sign of that first derivative is in those 4 different intervals, right? So the first interval is this one, and yeah, so we have -3. I plug it in those 2 places. -3, the bottom is positive, the top is negative, so the whole thing is negative. And yeah, let me make it blue, so negative. Right, so negative means the function is decreasing. Right, so the second testing number is -1, and again, right, we plug it in, and you probably see that right, the denominator is always going to be positive, right? So everything will depend on that numerator. So I can see already that it's also going to be negative, so no change there. And then for positive no 1, right, it's going to be positive, because, well, 1 is a positive number, right? So positive, 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 function increasing. And now between so now we were testing for 1, now I'm testing for 3, and the same thing, right? I didn't even need to test it because I know the bottom is always positive. So this is the situation here. So the function is increasing from -infinity to 0, and then from 0 to positive infinity. Did I say increasing? I meant decreasing. I don't remember what I said. Anyway, so one more time, from -infinity all the way to 0 is decreasing, and then after that is increasing. Okay, so that was the first derivative, and then let's analyze that second derivative. So step number 6, second derivative. Analysis. And again, right, so I'm going to write it, right, that second derivative. So I have double prime of x, and it went something like this. It's -20, and then the top is I mean that parenthesis 3x squared plus 4. Okay, and the bottom is x squared minus 4. And that's to the 3rd power. Okay. And again, right, so we draw the number line. And we put those numbers, right, critical numbers again. So we have 0, 2, -2, and so do we have the same testing numbers, so -3, -1, 1, 3, and yeah, so again, right, we're testing -3 in 2 places, and we see that the top, right, is going to be always negative, so that's always negative. The top is always negative, and the bottom will be changing. Yeah, so let's start with that -3. So -3, right, the top is always negative. The bottom is going to be, in this case, positive. So negative over positive, so that's going to be negative. So negative was blue, I believe. Okay, so we have negative. And we're testing the second derivative, so negative was concave down, right? Okay, then we have -1, right? We're testing this interval, and so negative is our testing number. Plug it in. So it looks like the bottom is going to be negative, right? Because I have 1 minus 4 to the third power this time. The top is always negative, so negative over negative, I'll have positive. Okay, so we have this interval is all positive. So that's concave down, sorry, concave up. And then for 1, right, we'll have the same situation. So plug in 1, and again we'll have positive, right, because I have negative over negative. So again, concave concave up, right? I'm thinking about that minimum, right, that there's gonna be I'm gonna have a minimum at 0, and that's why I'm just kind of messing up that concave down, concave up. Anyway, and that for 3, I'm going to have negative on the top and positive at the bottom. So we have negative. Okay, so concave down again. So what I'll do, I'll erase these two, and I make it just one, okay, one symbol for concave up. Okay. All right, so let's look at maybe the inflection numbers, right, quickly. So it looks like there aren't any inflection numbers because right, so to get the inflection number, we would make it equal to 0, right? Or inflection numbers, or candidates for inflection numbers, and we need to figure out well, what numbers, what x's would make it equal to 0, right? So is there anything I can plug in there to make it equal to 0? Well, the answer is no. And then, right, for these two, again, the problem here is that 2 and -2 are not in the domain. Okay, so there are no inflection numbers because they have to be in the domain. So let's graph it. So number 7, graph. And yeah, it's not easy, but we have a lot of information, right? So we start with the asymptotes. So we have 3 asymptotes, right? So that's one of them. That's -2. Second asymptote at 2. And the last one, I think, I don't remember. Yeah, it's also 2. Or let's make a dashed line. Okay, so dashed. All right, so we need to fit that graph somewhere, right, between those asymptotes. And we have x-intercepts, so there are 2 of them, -3 and 3. And y-intercept was 9/2. So that, what is that? 4.5. That's let's make this 4.5, so 9/2. And well, what else do we know? All right, so we have those asymptotes. So the graph needs to get closer to those lines, right? So something like this. You could find a couple other points if you want to graph it more better, more exactly. And then, right again, right? I need to get closer to those asymptotes. Okay, and the last branch looks like this. Okay, so yeah, I just kind of graphed it, but in general, right, it's quite difficult. But let me just point out a couple things. So first thing, and we have concave down. So that's this part. That's in, like, for me, this is the probably the most important information, right? Concave down. Also, function is decreasing over there. Then over here, right, we have concave up. Right, so that's this section, concave up. By the by the second derivative test, we know that this point over here is a local minimum, right? Because 0 is a critical number, right? And f double prime of 0 gives us a positive number, so concave up, and that 0 is x equals 0 is that local minimum. It occurs at that, right? The value is 9/2, but it occurs at 0. And then the last branch, right? Again, we have concave down. That's over here. X-intercept is 3, and that's the graph. Okay. I have what do I have? I have one more example for you. That you could try that example by yourself, but well, you could treat it as a practice problem. But I'm going to go over it. Okay, so example 2. So again, analyze and graph. And graph. And we have, here's the function. 2x 5/3 is the exponent there. Minus 5 x 4/3. Okay, so yeah, this is yeah, the calculus for that problem is actually pretty doable, pretty simple. I mean, it's not simple, but I think the algebra part is actually like finding intercepts, right? This is actually quite difficult, right? Because we'll have to solve, we'll have to make it equal to 0, right? To find x-intercepts and then solve it. I don't know. it's not easy. Anyway, yeah. So let's start with the. So yeah, you can pause the video and yeah, try to do it yourself, right? Go through the same process, the same steps. Okay. Yeah. So the first derivative, f prime of x. Yeah, I said, the calculus for that problem is easy, but actually, like just even taking the derivative of that is not that trivial. Anyway, it's easier than the previous example, right? Anyway, so maybe quickly I'll just go over that first derivative, right? So 5/3 goes to the front, right? I still have that 2, and then I subtract 1, right, from this fraction. So 5/3 minus 1, so that's 2/3, right? 3/3 minus 5/3. I mean, 5/3 minus 3/3 is 2/3. So 2/3. And similarly with the second one, right? So I have that 4/3. Then we have 5. And then we have 5. We have x. And here we have, this is 4/3. minus 3/3, 1/3 is left. Okay, so let's clean it up a little bit. So f prime of x. So we'll have 10/3 x to 2/3 minus 20/3 and then x to 1/3. What can we factor? We can factor 10/3 x to 1/3. Yeah. Anyway, f prime of x. Right, so I'm factoring 10/3, right? So that's quite easy to see, right? What I did, what I'm doing, right? I'm factoring 10/3 from these two numbers. So out of that first number, let me just, for some reason it got darker, for me at least. Okay, so I have 10/3, and then I said I'm going to factor x to 1/3. Right, so now the big question is, what do I have left? Right, so think about it. What do I have left in the parentheses? Well, out of that second, I'm factoring that, right, this whole thing, x to 1/3. So, and then I'm factoring that 10/3. So I have just 2 left. Right, so I hope that's what you get. And here, that's what I have left, right? So if you check it, right, if you distribute that to both, right, it's pretty difficult algebra. I mean, it's not difficult, but anyway, people tend to forget. So yeah, when I'm multiplying these two, right, remember when you multiply two variables, right, the same variables but different exponents, we add the exponents, right? So x to the 5th. So that's what happened here, right? So if you multiply these two, x to the 1/3 times x to the 1/3, you add the exponents and you get 2/3, right? So that's how we got that. All right, so that's the first derivative. I don't know, I don't have the second derivative here yet. I guess I did it later. So that was the first step. No, the first step was actually intercepts. So let's go there, intercepts. Okay, so we have, yeah, so I strongly recommend you try to solve this, right? It's not trivial. I'll show you in a moment. 0, 0. I mean, I'm not going to solve it for you, but I will show you what you need to do. 125/8, right? So these are the two x-intercepts. And yeah, right, we're finding x-intercepts, so we're making y equal to 0, right? So we're here. To find intercepts, right, we're not using first derivative or anything like this, right? So just take the original function. So 2x to 5/3 minus 5x to 4/3. Yeah, and make it equal to 0, right? And try to solve it. It's not trivial. Anyway, so yeah, so this was the x-intercept. So now y-intercept will be just that 0, 0, right? So 0, 0 is the y-intercept. And yeah, to find it, just plug in 0, right? And you get 0. Okay. What is the next thing? Asymptotes. So this is not a rational function. It's not really a polynomial, but almost. Yeah, so we're going to say no asymptotes. Okay, so now we have those critical numbers. So step number 3. Okay. Yeah, so to find critical numbers, right? I hope you remember, we just reviewed that. Or critical points. We take that second derivative. Okay, so what is the second derivative? Oh, it's up. Sorry, first derivative. So 10/3 x to 1/3, and then I have x to 1/3. And again, right, it's not easy to solve. Make it equal to 0, right? So we solve it, and yeah, use it as an exercise, right? So try to figure out how to solve it. So the first critical number, it's actually yeah. So I have it as critical points. Let's keep it as numbers. So let me get rid of that thing. So we're just going to make it x equals 0. Right? So that's one of the solutions. And then the other one, x equals 8. Okay, so we have that first derivative. We have critical numbers. There are 2 of them. So let's do the analysis of the first derivative. So this is step 4. So 4, analysis of first derivative. All right, so number line. We have 2 critical numbers, 0 and 8. So let's be consistent. Well, be consistent. So 0, 8. And then let me write that first derivative somewhere. So where is it? Okay, it's here. So you have f prime of x, so 10/3, and then x to 1/3, x to 1/3. So by the way, write that and 1/3 is a cubic root. Okay, that's just that. All right, so here's the first derivative, testing numbers, and -1, and then this could be 1 and 9. Okay, so what do we have for -1? For -1, so cube root of -1, right? So I'm looking at this is -1, right? So -1. So this is so this is going to be negative, and now this part is going to be also negative, and because I have again cube root of -1, right? So again -1 minus 2 -3, so negative times negative is going to be positive. Okay, so that interval is positive, so the function is increasing. Okay, so now I'm testing for 1. For 1, this will be positive, this will be negative, so the whole thing is negative, right? Negative times positive, negative, so this interval is negative, the function is decreasing. Okay, and then testing for 9. I'm not sure what the cube root of 9 is, but it's a little slightly more than 2, right? Cube root of 8 is 2, so cube root of 9 slightly more than 2. So that means that this will be positive. This will also be positive, right? I'm subtracting 2 from something that's slightly bigger than 2. So I'm going to get a positive number. So the whole thing is positive. Okay, so this was the first analysis first the analysis of first derivative. Let's look at the analysis of the second derivative. And again, right, so you guys can figure that second derivative on your own. Pause the video. Right, so it's all about getting comfortable with taking derivatives, right? So that's what the first calculus 1 is all about, right? I mean, not only, but pretty much. Okay, so this is the second derivative. That's what I got. Divided by 9 times x to the power of 2 over 3. 2 over 3. Okay. Okay, so we make it equal to 0. Right, so next step would be to find those possible inflection points. So possible inflection points. Okay, so what are they? Let's just look at it. So the first candidate would be 1, right? Just kind of look at the numerator. What do I put in for x to make it equal to 0, right? So that answer is 1, because cube root of 1 is 1. 1 minus 1 is 0 times 20 is still 0. Okay, so that's one of the candidates, one of the possible inflection points or numbers, x equals 1. And the other one comes from denominator, right? So number that for which the second derivative is undefined, right? So it comes from here. So that'll be 0. Okay, so we have two options to candidate for those inflection points. And yeah, let's do the analysis, right? So second derivative. Well, actually, this is what that is. I didn't write it there. Anyway, it should be here. So analysis of second derivative, right? It could be where it is, or could be here. Anyway, so we do the number line. And what I'll do, I'll put, right, so I have those inflection points or candidates for them. And I also have that those critical numbers. So critical numbers were 0 and 8, right? So those two overlap. So we have 0 here. Let's make it blue. Again, 0. And then I believe we had 1 and 8. Right, so 0 and 1 are candidates for inflection points numbers. And then I think, yeah, 0 and 8 are critical numbers. Okay. Yeah, so now I'm picking those testing numbers, right? There's so many different names. So let's pick, this could be what? Half. And the simplest number here would be 2. And 9 here. Okay, second derivative. Where is it? Yeah, it's there. I can use it. Okay, so for negative 1. For negative 1, I think we get negative. Let me just kind of look at it quickly. Okay, so I'm plugging in negative 1. Right? I'm looking at this. I'm looking at this. So negative, so this denominator will always be positive, right? Because even though I'm taking a cubic root, so if I'm taking a cube root of negative number, I still have a negative number. But then, or before, right? Doesn't matter. I'm squaring that number. So I could either take a cube root of that negative 1, so negative 1, and then square it, right? So that would end up with 9 at the denominator. or I can square it first, so positive 1, cube root 1 times 9, 9. So positive, this will always be positive, so I'm going to put it over here. Right? Always positive. And now, yeah, I'm taking cube root of negative 1 over here. I'm over here. Right? So negative 1, cube root of that, negative 1, minus 1, negative 2. So negative number, right, on the top. I'm going to erase it, but for now. So this part is negative. And yeah, so the same, I'm going to get negative, I think. Maybe not. Hold on. Yeah, also negative, because right, I'm plugging half, so I'm plugging it over here. Right, so cube root of half is definitely less than 1. So if I subtract 1 from that, I'm going to get negative number. So this is always positive, so I have negative. So this part is also negative. Okay. Now for 2, so I'm taking cube root of 2. So cube root of 2 is definitely going to be more than 1. So this will be positive also. So positive, so that's positive. Okay, so positive. And now for 9, also positive. I'm saying positive and I'm making a bunch of negative signs. So positive, 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 and positive. Okay, so the conclusion. So this will be concave down, and this will be concave up. Right, so you see what's happening, right? So I have one inflection point. I wonder if you know which one it is. Okay, so this is the inflection point, right, where my function will change concavity from concave down to concave up. Then we have two maxima, or sorry, two extrema. So I have 0 will give me the maximum, local maximum, and this will give me local minimum. All right, so let's look at the graph. Put it on the next page here. I wonder if I can move it. Let's not waste time. Okay, so graph. No asymptotes. I have, so this was a local, I meant to make it blue. Okay, this was local what? Local maximum. Okay, local maximum. Then I had at 8. Right, so this was a local minimum. We had inflection point at 1. Maybe I'll put it, this is 1, so this is 8. Now this is not really in scale or anything. Then we had some other information. That was the x-intercept. X-intercept was 125 over 8. So that's 125 over 8. I have in my notes that that's about 16. Okay, sounds good. Yeah, so the graph looks like this. All right, so here I have that change, inflection point. This is minimum, local minimum. Then we have the x-intercept, and the graph continues up there. Okay, so this is local minimum, local maximum, And this is the inflection point. Okay, yeah, so that's the graph. And yeah, so the last thing I'd like to do is just give you a practice problem. Okay, so for practice, so here's the problem. So it's 3x on the top, and then x squared minus 1 here at the bottom. And let me just give you the derivatives. Okay, I'm not going to give you the graph, the solution. You can look it up somewhere, Desmos. So the first derivative, yeah, you can look up everything, right? X squared plus 1. And then x squared minus 1 squared. And again, right, I recommend, if you have time, right, if you want to learn calculus, right, you need to, this stuff needs to be easy for you, right? This derivative, second derivative. This is what I have. Positive 6x. And then x squared plus 3. And then the bottom is x squared minus 1 to the third power. This is second power over here. Okay. Yeah, so try to do this problem on your own. Let's see what you get. Actually, maybe I'll show you the graph. I'm just going to sketch it. And I'm not going to actually graph it. Two asymptotes, right? It's easy to see what they are, right? 1 and negative 1. So these are the vertical asymptotes. Is there a horizontal one? Yeah, there is a horizontal asymptote. It's this one. And it's, if you don't know how we get that horizontal asymptote, oblique asymptotes, right? So that's something you need to review. But basically the top, degree of the top is less than the degree of the bottom, right? So the horizontal asymptote is y equals 0. Okay, and here we have those two vertical asymptotes, right? X equals 1, x equals negative 1. And yeah, the graph looks something like this. Okay, so there's an x-intercept, y-intercept at the origin. And then we have two branches here on the left and on the right. Okay, so that's the end of this lecture. Yeah, that's it. See you next time.